Hello everyone, my name is Raghavi Priya, Assistant Professor, Department of Computer Science and Engineering. So in this video, you're going to see about principles of stereoscopic display in Unit 2, Visual Computation and Virtual Reality. So software and hardware technology on stereoscopic display. So understanding stereoscopic vision. So human stereoscopic vision relies on binocular disparity, the slight difference in images perceived by each eye. So this fundamental principle drives all stereoscopic display technologies. So the brain processes these disparate images to construct depth perceptions, enabling us to perceive three-dimensional space from two slightly offset viewpoints. So core hardware technologies. So polarization system. So linear and circular polarized light separations enables passive 3D viewing with lightweight glasses. So active shutter display, time sequential presentation synchronized with LCD shutter glasses for high resolution stereoscopic imaging. So autostereoscopic displays, lenticular lenses or parallax barriers provide glasses free 3D viewing through spatial light modulation. So stereoscopic rendering pipeline includes scene geometry processing, stereo camera configuration, dual viewport rendering, display output processing. So scene geometric processing include 3D models which undergo transformation matrices for dual camera perspective generation. So stereo camera configuration includes intraocular distance and convergence angle calculation determine optimal viewing parameters. So dual viewport rendering, simultaneous left and right eye image generation with precise temporal synchronization. So display output processing includes frame packing, side by side or interlaced formats, prepare images for hardware presentation. So critical distance parameter. So 65-meter average IPD, that is interpupillary distance variation, affects stereo comfort zones. So 120 Hz minimum frequency for flicker-free activities, that is system, so which is a refresh rate. So 1 parallax tolerance, maximum comfortable disparity before eye strain occurs. So software architecture components include graphic API integration, then stereo driver layer, application framework, performance optimization. So graphics API integration includes OpenGL, DirectX and Vulkan extension enable stereo rendering, context and multi-viewport management. Stereo driver layer includes hardware abstraction, manages display synchronization, format conversion and device-specific optimizations. So application framework, high-level APIs provide stereo scene, graphic management, camera control and user interaction handling. So performance optimization, custom culling, level of detail algorithms and temporal coherence techniques maintain real-time frame rates. So disparity and depth mapping. So negative parallax, object appears in front of the screen plane, creating pronounced depth effects but requiring careful comfort zone management. In zero parallax, screen plane positioning provides us the most comfortable viewing experience and serves as the convergence reference point. So in positive parallax, behind the screen, depth placement extends the viewing volume while maintaining visual comfort. So advanced rendering techniques include asymmetric frustum projection, temporal reprojection and adaptive quality scaling. So in asymmetric frustum projection, off-axis projection matrices eliminate keystone distortion while maintaining proper perspective geometry for each eye. Temporal reprojection. Motion vector analysis enables frame interpolation and reduces computational overhead in complex stereo scenes. So next, adaptive quality scaling. Dynamic resolution adjustment maintains target frame rates while preserving visual quality in performance critical applications. So performance optimization strategies. GPU parallelization, simultaneous left or right eye rendering using multiple render targets and geometric instancing techniques. So level of detail management, distance mesh simplification and texture resolution, calling optimized rendering performance. So occlusion culling. So per-eye frustum culling eliminates unnecessary geometry processing and reduces bandwidth requirements. So next one is temporal coherence. Frame-to-frame consistency algorithms reduce computational redundancy in dynamic scenes. Future directions. Holographic displays. Light field technology promises true volumetric imaging without accommodation, convergence, conflict. AI enhanced rendering. So machine learning algorithms optimize stereo parameters and predict optimal viewing configurations. So quantum processing. Quantum computing may revolutionize complex stereo calculations and real-time depth synthesis. Gaze adaptive system. Real-time eye tracking enables dynamic convergence, adjustment and foveated rendering optimization. Thank you.